Okay, so welcome back. This is actually, what the hell? Lecture 4 of Electronics 2. And I've been busy the past 2 weeks trying to juggle my own courses because like you probably already know, I am going through a semester myself, taking 6 classes. So being consistent with making these videos becomes a little bit of a challenge. However, I'm still going to push myself to make them because I'm getting the views, and then people are really getting something out of it. I have gotten a request to make a video on current mirrors. The thing with that is just I don't have my notes prepared for that yet. So I usually go back to my own notes when I was taking the class, the way that had me understand. And current mirrors, like I said, it was a pretty straightforward topic, so I didn't go in depth writing my own notes about it when I took the class. So I'm gonna have to write that down, and as soon as I have those prepared, I will post a video about current mirrors. But today we're just gonna move ahead, like past differential amplifiers, and you guys probably saw like common mode rejection ratio and all that stuff. It, it's not that prominent on the final exam. I think, like my style, like in electronics one, I'm just gonna cover stuff that's gonna be the bulk of your exam and the bulk of your evaluation. In my opinion, those things are not that important. It might be a multiple choice question here and there, but not really anything big and conceptual. So current mirror is going to be coming in the future. Today we're going to look at Miller multiplication for capacitors. So let's get started in that. Now, if you remember from electronics one, well, when doing AC analysis of BJT and MOSFETs as amplifiers, all these capacitors in your circuit pretty much went to a short circuit because we assume very high frequency when these capacitors are essentially shorted, and then you can do analysis from there. However, in reality, that's not totally the case. Those capacitors have an effect, and we need to consider those effects because it has an impact on your gain. Because if you look at here, I'm just going to show you here. So I'm going to go down and I'm going to make a little bit of a graph. Let me do this in blue. So if we do have a graph here, and from circuits theory 2, you've probably seen Bode plot. So if this is my frequency omega, and then this is my gain, 20 log base 10 of the absolute value of the transfer function. You should probably have seen this in circuit theory. This is essentially your gain. You take the absolute value of it and you take the 20 log of that value because you want to get your values in decibels per decade. And usually, if you do not have any capacitors in your circuit, whatever value you have here for your gain, let's say it's this value, it's going to stay pretty consistent. However, in reality, your circuit, especially in this course, we don't have any zeros, so you're not going to have a gain that's going to go up. So the only thing we consider in this class is zeros. So we want to see where a gain starts to attenuate. So there might be different points where your gain starts to attenuate. It might be something like this. Your gain actually might be something like this. Here, and then here, and then here, and then here. Something like that. So your gain goes down. And these points where the gain starts to go down are called poles. And what's responsible for these poles, you might guess it, capacitors. So you can do AC analysis with AC hybrid pi model with the capacitors in there. Same thing with the BJT, and then write V out over Vn. However, that is not efficient, and mistakes are going to be made. Like it's terrible to do AC analysis with capacitors. So we have methods that we can implement to make our lives easier. We need to find those poles. So there's something called the pole identification technique. And to be able to apply those, we need Miller multiplication of capacitors. So now that I've motivated the importance of capacitance and why we need to consider that, we'll go and learn about Miller multiplication of capacitors. However, one more thing that I wanted to mention is that once you know the effects of these capacitors on your circuit, you can know the bandwidth of your gain. In fact, you want to maximize your bandwidth. You want the you want the you want to range in your frequency from say x value till y value. You want to make this x value and y value as far apart from each other as possible so that your gain stays consistent. So that means you want to place your pole at the extreme of the y, and if there's any at the input, you want to put it at the extreme close to the zero. This way you're maximizing that stable gain that you need. Okay, so let's go back here. Miller multiplication for capacitors. So let's say you have a certain circuit here, and then you have a circuit going on here with a gain AV. All right, that's just a random circuit, could be anything. And this is AV, And the equation of that gain is V out over V in. So here we have our input voltage, here we have our output voltage. Across of the circuit, in parallel, we have a capacitor, and its value is denoted by CF. Now, if you want to use pole identification technique, one of the key things that you need a capacitor that's connected to your circuit at one point, but at the other point is connected to ground. If you look at the situation here, you have the capacitor connected to the V input, and the capacitor on the other end connected to the V output. You have nothing that's connected to the ground with that capacitor. It's not something like this. Oh crap. It's not something like this. We want something like this. So we'll use a technique of Miller multiplication for capacitors to obtain something like that. As I've said before, if you look at the circuit, we have successfully done that. So if you look over here, this is the gain of your circuit, and then this is AV and your circuit itself, like whatever circuit you got going on here with gain AV. And then this side on the left of the capacitor, the gain, the left of the capacitor, the left of the circuit, the gain is going to be CF times 1 minus AV. Now, what is AV? AV is the AC small signal gain of circuit. So what I want you to do is, when I say AC small signal gain, is how do we calculate AV? Is V out over V in. But how are we going to calculate the gain if the capacitors are present? So that's the point. We're just going to ignore the existence of that capacitor. We're going to compute a regular gain, all right? And then what we want to find, we don't want to take that CF and split it into two. The capacitor on the left is going to be CF times 1 minus the gain that we calculated without the capacitors. And on the other side of the output is going to be CF times 1 minus 1 over the gain that you computed of that circuit without the capacitance. That's the key word here. When you're trying to find AV, we're approximating it by ignoring these capacitances and computing the gain of that circuit. And this is where I think memorizing the gain equations of the common circuit are very, very important. Common source, common drain, and common emitter, common collector, common base, common gate, all that thing. Memorize these gate equations, because most of the times you're going to have a capacitor that's connected between the input and output of such amplifiers. And then if you know the gain, you don't need to do any analysis. You know that, hey, without a capacitor, this is my gain equation, so I can take that and replace it for AV. Nice and simple. It saves you like 10 minutes. So do memorize that. That's a pro tip. So now, finding poles using pole identification. How do we do that? So we have a couple steps here that I wrote down, and these are pretty very easy to follow. And if you follow this step by step, you won't make many mistakes. So first of all, it's important to understand how is pole identification used. Where does it come from? You're not going to see a derivation for that, but I will tell you right now that pole identification comes from a subcomponent of Thevenin equivalent circuit, right? You have a capacitor, and something related to Thevenin leads to pole identification technique and the capacitor separation. So when you're doing Thevenin, all of the sources you're going to disable, right? So in this case, you're going to disable the DC sources because it's AC. You're doing AC analysis, and then you're also going to disable the DC. That's what I said here. So Vin is also disabled during pole identification, since we disable all independent sources when doing Thevenin. So doing Thevenin, so all independent sources, whether AC or DC, will be disabled. And then you want to spot all capacitors in your circuit. And then first, you want to deal with all the capacitors connected to ground at one point. Say, for instance, we had a capacitor that's connected to ground here. You want to deal with this one first before moving on to this one. Okay, so deal with the capacitors at ground first, because they're basically free. You have no work to do there. And then you will apply Miller's theorem for ungrounded capacitors. So now, like I said, you're going to have capacitors that's connected to ground. You're going to deal with them first. When you have ungrounded capacitors like this one, that's when you'll use a new technique, split it, to make them into capacitors that's connected to ground, and move on with your analysis. Now, very, very important. How do we spot the poles of a circuit without doing crazy analysis? This is the key point here. All the capacitors that are connected to ground on one point, or all the capacitors connected to ground. Well, that's not. It doesn't have to be connected to ground. All the capacitors that are parallel to a resistor is gonna produce a pole, right? So if you have a capacitor in parallel with a resistor, that's gonna produce a pole. So when you're looking at your circuit, you want to look at all the capacitors and ask yourself the question: is that capacitor parallel to a resistor? If yes, it's going to produce a pole, and then you write the equation of that pole. So here, we're going to look at an example to make everything clear. We have this circuit going on here. All right, we have RS, RD, and VL, VN. This is a MOSFET, and you will notice that we have a capacitor connected from the output and the input of this circuit. Well, input technical right here, whatever. Doesn't really matter that much. This is the input. Okay, so as you can see, is you want to disable all of the DC sources. Okay, so this was VDD, DC, it's been disabled right here. Spot all capacitors. So this is my capacitor. Deal with the capacitors connected to ground on one node first. There is no capacitor connected to ground, so we'll move on to the next step. Applied Miller's theorem for ungrounded capacitors. So if you look over here, we have CF, and then AV in this case is this. All of that is AV. All right, all of that is AV with the input here and the output here. So this is going to be this, and this is going to be that. So CF1 right here, this capacitor, is going to be replaced by this equation, and CF2 here, this capacitor, is going to be replaced by this equation. But we need to find AV. So again, let me reiterate here. We have this ungrounded capacitor. We're going to split it into two capacitors connected to ground, one here and one here, CF1 and CF2. That's what I denoted it as. CF1 is going to be replaced with this equation, and CF2 is going to be replaced with this equation. Okay, but we need to find AV. So this is the equation for CF1, CF2. What is the equation for AV? So if you memorize the equation of a common source, you will see that, hey, the input is given at the gate, the output is taken at the drain. So the only thing that's remaining is the source, so it's a common source circuit. So the gain of a common source is minus GMRD. All right, you can get it from there. So you already know what AV is. AV is minus GMRD. That's how beneficial it is to memorize these gains. But if you do not know that, you're going to have to derive it yourself. So finding the gain, if you don't remember the gain of the common drain. Right, this is common drain. This is common source. I don't know why I wrote common drain here. Output ticket at the drain, input given at the gate. Yeah, this is common source. What the hell am I on? Guys, I don't smoke weed, by the way. This is just a regular mistake. I don't usually make mistakes like that, but sometimes it does happen. So common source. Okay. So this is a common source transistor, common source circuit. So we're just gonna have to calculate the gain, and I'm gonna use like a hybrid of electronics 1 and 2 methods to do this. So the gain is minus GM or out, and as I've said before in my previous lecture, GM most likely will be equal to GM. So I'm just gonna go straight from here and use it there. And now we need to calculate our out. So I'm gonna draw a small signal model, gate, source, drain, and then the drain is connected to RD right here, and the gate is connected to ground because we're doing our out. We're finding the output resistance. So if you notice here, VGS is equal to 0 because the gate is grounded and the source is grounded. So that means VGS is equal to 0. So your circuit simplifies to this. And because we're given in VT here, we 1 ampere current inside of your circuit, VT will be equal to RD. So your gain is going to be equal to minus GMRD, which is basically what we have here, if you do not remember the gain equation. So now all we have to do is take this AV and replace it into our capacitor equations right here, which would mean that CF1 is equal to 1 minus GMRD CF, and CF2 is equal to 1 minus 1 over minus GMRD. So this is equal to 1 plus GMRD CF and 1 plus 1 over GMRD CF. So this is your equation for the capacitor 1, equation for the capacitor 2. So if you go down here, now you can basically ignore this capacitor because you know the equations and the value of these capacitors right here that are connected to ground. Now that you've reached this step, this has been dealt with. All the ungrounded capacitors have been grounded using Miller's theorem. Now, you want to see and ask yourself the question, are there any capacitors that are connected to in parallel to a resistor? So if you look over here, this capacitor here shares the node with this resistor RS, and on the other side is grounded. This is grounded. So these two are in parallel, right? This is basically the same point, and this is a parallel combination. Again, this capacitor here is connected to this resistor already on one point, and the other point is grounded. So this is in parallel too. All right, so we have a capacitor in parallel with RD and a capacitor parallel with RS. So these two capacitors are both going to produce poles. And what is the equation of a pole? The equation of a pole is 1 over the resistor times the capacitor. That's basically it. And in this case, since we have a pole at the input and at the output, I'm going to call it omega in and omega out. So that's going to be equal to 1 over RS or CF1, 1 over the resistor times the capacitor, and W omega out is going to be 1 over RD times CF2. So 1 over RD times CF2. Now CF1 and CF2, I just replace them by their necessary equations, and here I get this, and I get this. All right, so this is what I do have, and these are equations of my pole. So if you look over here, what does that mean in terms of a graph? So these are the points here. This could be omega in, and this could be omega out. I don't know exactly. Omega out could be before omega. I don't know. I don't really know how it works because I don't have the numerical values. But what I'm trying to get at is these are the points on the omega axis where your gain will start to go down by 20 decibel per decade. Now you get it. So now it's the point at which your gain is no longer stable. It's no longer a regular gain minus GMRD. It's going to be minus GMRD until it hits that first omega in or omega out. It starts to dip. And it's going to be that gain that's dipping until it reaches the next pole, and it's going to dip again. All right, and that's it. Your gain is like this. So then you're going to notice that your circuit works as an amplifier only between two different points. All right, at some point, you're not going to have any gain because you're going below zero, right? Your gain is going to reach attenuate goes to zero. And there's only 2 points, arranged between 2 points where your gain is steady. And that's what you want. You want to maximize that bandwidth. So this is the intuition. I hope I was able to cover as much intuitive methods as possible to solve these circuits, because it's very easy to be like, hey, well, what's the point of Miller's multiplication? What's the point of capacitors? Blah, blah, blah. Why am I doing this? Why is this and that? So here's the point. Why are we doing this? How do we do it? And how do we do so correctly? So with that being said, this is lecture 4. This one I recommend you rewatch it. It's a very important question, guaranteed question on the final exam, similar to this one, 100%. So watch it again. You have questions, comments. All right. Have a good, productive reading week.